Welcome back, everybody. I see people are coming in fast and furious in the popcorn of Zoom. It's a treat to be introducing today Nadia Fawaz. Actually, I introduced her really at the end of the last session, but let me just do so again. Nadia, I told everybody I'm doing non-standard intros, so I hope you're okay with it. Again, these are such distinguished speakers that they don't need me to introduce them. But really, interestingly enough, at the end of the last session, I realized Zara from Intel identified recommendation systems as really sort of the best application, the most promising field of use for all these matters around networking and machine learning. And so you're the perfect segue to that. That was not set up, but had it been set up, we could not have set it up better. The other thing that that I mentioned is, of course, your longstanding work and dedication to really taking a humanistic view of technology, humanistic really in its best sense, human-centered, with respect of the user, whether that be privacy or their preferences, respect writ large. And inclusivity, of course, is one of those core aspects of respect. So I'm thrilled to have you among our speakers, and I'll cede you the floor and the screen. Welcome.
Thank you very much. Thank you very much for this very kind introduction, Muriel, and thank you, Muriel and Mania, for inviting me to speak today. So I'm an applied research scientist and the tech lead for inclusive AI at Pinterest. And the work I'll be presenting today about inclusive search and recommendation is a collaboration with wonderful peers from many organizations at Pinterest. So AI powers many advanced search and recommendation systems, such as those at Pinterest. And these systems consist of several machine learning models, including deep neural networks and graph-based machine learning. And in a nutshell, these models are trained to predict the likelihood that a pinner, we call our user pinner, would interact with a piece of content, a pin, and it takes as input queries. And at Pinterest, our data is multimodal, so queries can come in the form of text typed by the user, images that the user input, or they can be an entire pin, which is an image with a title, a description, and a link to a website. Those models take also user features, such as the interests the pinner follows, content features, the image, the description, and past interactions with pins and boards that have happened on the platform. And once these models have generated that prediction score about how relevant the pin is for a user, they rank those pins by those scores and they surface them to the user in the interface. Now, these systems tend to be very complex. They have several components and layers of complexity, and they need to operate at scale so that users can get their results and recommendations in a fraction of a second when they open the app. And we work at very large scale at Pinterest. We have over 454 million global monthly active users who have saved 300 billion pins to more than 6 billion boards in 30 languages. And luckily, most of our pinners think that Pinterest is a place filled with positivity. Now, Pinterest vision is to bring everyone the inspiration to create a life they love and to truly be a place where everyone can find the most inspiring and relevant content to them. Pinterest is committed to content diversity and to developing an inclusive experience on the platform. Now, the goal of my team, the Inclusive AI team, is to make our AI systems perform outstandingly well across our diverse set of users, including pinners and content providers, and our wide range of use cases. AI learns what we teach it to learn. And if the data we input in those systems is not diverse, the AI models may learn implicit biases, serve biased results in productions, leading to collecting more biased data. And this is the creation of a biased feedback loop. And so we would like to move towards a virtuous cycle where we start with diverse data, we mitigate potential biases in the systems, and we make the user experience more inclusive. Now, developing inclusive AI requires an end-to-end iterative approach where we collaborate with several organizations. We have learned the importance of building those systems in an inclusive manner by design, of measuring to make progress, and of leveraging both artificial and human intelligence. And we recognize that these challenges are multidisciplinary, not just technical. So we work, as I mentioned, within a large cross-functional team that enables engineering to work with other organizations. So during this talk, we will go over sources of bias, how we can reduce this bias, and then I will describe how we developed two of our inclusive features at Pinterest, the skin tone ranges and the hair pattern search. Oh. Okay. Biases can arise at different stages in ML-based recommender and search systems. So it can start with societal biases that are inherently present in the data before we do anything with it. So this table on the left comes from a study by the Pew Research Center. It shows that the mix of users according to their demographics in various online platforms is actually different. There are many diversity dimensions we can consider. Some popular ones are usually demographics, such as age and gender, but they can be geographic and cultural, country and language. They can be application specific, skin tone for beauty, or sometimes the diversity dimensions cannot be explicitly expressed as a combination of those explicit dimensions are rather implicit and require latent representation. And because we have a different mix of user, this has an impact on the content available on the platform and how users interact with the content. Now, biases can also be introduced by the data collection process. So, for example, serving bias arises when some samples are less likely to be included than others. In production systems, that comes because the content that is surfaced depends on the current machine learning model that's operating in production. And items that it doesn't surface, well, we cannot collect feedback on them. Position bias is due to the user's propensity to pay more attention to the top left corner of the screen and interact with those results more than with other results on the page. Summary-based presentation comes from users' propensity to pay more, to favor and click on items that they deem more attractive as per their visual component or their summary. And repetitiveness bias comes from users' fatigue as we show an item over and over to them. So you see in this curve the click-through rate that decreases as an item is impressed many times to a user. Now, the biases can also come from the modeling choices that are made. And here I would like to make a distinction between two types of biases. So people are usually familiar with statistical model bias that may arise when the complexity of the model is not appropriately chosen to fully represent the data. For example, the too simple model with not enough parameters. And this type of bias, it cannot be solved by providing more of the same data. So imagine, for example, that your data is generated by some quadratic and you're trying to fit it with a line. No matter how much data you give it, the line is not going to fit perfectly the quadratic. And so this happens usually in the top left corner of this graph, or if you prefer the more modern graph, the area of underfitting. Now, this is different from algorithmic bias in the machine learning fairness world. This is concerned with mitigating disparities in performance for different groups according to a diversity dimension or a sensitive attribute. And these biases can come from various choices. It can come from a training objective that's focused on a single utility or an aggregate loss function that favors the majority. It can come from the model structure or its subcomponents. For example, if a system consists of several components and one of them has bias, the bias may propagate to the rest of the system. Or it can come from the phase of hyperparameter tuning and the way we tune those parameters. Now, after we've collected data and we trained a model, we usually perform offline evaluation of the model on a data set. And this allows us to evaluate if the model can generalize to unseen data, and also to iterate fast on models before we productionize them and make them serve live traffic. So that allows us to rule out models that did not perform well and not expose our users to them. Bias in offline evaluation can happen because the offline evaluation data is imbalanced or lack proper coverage, or it may be because the data comes from human labeling and every one of us has their own biases, so the labeling itself may be biased. It can be because the world is not static and the data distribution has changed between the time it was collected and the time we're evaluating. And it could be because the evaluation metrics that we are considering are coarse overall aggregates. For example, accuracy is dominated by the majority class. So I'd like to give you some intuition by using a toy example. So imagine there are these two groups, one large group A and one smaller group B. And in group A, most users prefer red apples. In group B, they prefer green pears. And we have this imaginary algorithm that looks at past data and learns that red apples are the most popular fruit. So it now always recommends red apples. So what is the performance of this algorithm? Let's look at its accuracy. It's 74%, seems to be doing okay. But if we take a closer look at how it performs for each group, we see that there is a gap and that errors disproportionately affect the smaller group B. And so mitigating the disparities in performance between groups is the main focus of ML fairness. So now that we have a model that has been evaluated and we want to put it on production traffic, we usually run an experiment, an A/B test. And the way we run these experiments could also potentially introduce bias. So these graphs are from an experiment run by colleagues of mine. The left graph shows the proportion of users in the experiment in 3 groups. You have the core users who engage frequently with the platform, the casual users who engage a little less, and then marginal users. And what you see is that over time, the distribution of users in the experiment changes. At the beginning, you have more core users, and later on, as time passes, casual and marginal users proportion increase. And the right graph shows how the lift of the new experience relative to the control evolves over time. At the beginning, when the core users are the large proportion, it seems to be a gain, but if we wait long enough for non-core users to appear, the lift eventually becomes a loss. So too short experiments can lead to the wrong conclusion. Now, how can we address these biases? There are several techniques that can help reduce bias at different stages of a machine learning system. A common way to address serving and position bias is to use randomization techniques. A simple example is top K randomization, where you shuffle the top results at the top. A more economical approach is to use explore-exploit techniques, which alternate between 2 phases, an exploitation phase that selects items with high predicted scores according to the current model, and an exploration phase that takes an intelligent risk to serve items with a lower predicted score. And these techniques allow to surface at the top items that otherwise would not appear, and give us a chance to collect feedback on them and help the model learn on the long term. Another approach is diversity re-ranking. So here the idea is to make the set of items served more diverse, and there are various ways to re-rank the items, but they try to make the result, the recommendation distribution over the sensitive attributes satisfy a certain diversity distribution target or a certain fairness requirement. Now, one approach that I will talk more about in details in the second part of the talk is to give actually control to users over their experience. And one example is those inclusive filters. So a top request we've heard from pinners is that they want to feel represented in the product. And this is why we build the skin tone ranges and the hair pattern search, which are inclusive search features that provides users the option to narrow beauty results by a skin tone range or hair pattern of their choice. These filters have also been deployed in the AR try-on similar look recommendation module to help make this experience more inclusive. Now, beside those techniques that are used at serving time, at the time of modeling and evaluation offline, we can also augment the data, either by making the data set more diverse through manual labeling, or by using data transformation techniques to augment the data set, or by revising the way we sample positives and negatives for our prediction tasks. The modeling phase can be augmented. In pre-processing phases, common ways are to change the way we sample or we weigh items based on the class they belong to. The model itself can be revised, changing its structure, changing the subcomponents. The objective that is optimized can be changed. Constraints for fairness can be added. And the post-processing phases, such as hyperparameter tuning, can be also performed in a fairness-aware manner. In offline evaluation phase, using a diverse data set with proper coverage is important. Going beyond aggregate metrics and breaking the performance metrics at a granular level per sensitive attribute and studying the error patterns is helpful. Going beyond the overall accuracy and using fairness notions to quantify disparities. And there are many open source tools that today offer a way of doing offline evaluation by being fairness aware. We've also found that bringing humans in the loop is very helpful, and also to measure in production and reevaluate over time the performance of systems. So now I would like to describe how we developed the Skintone ranges, the inclusive feature at Pinterest. So until in the early days, to understand the skin tone in a beauty image, we considered a closed box computer vision library composed of several modules. It had a deep learning module to do face detection, followed by a color extraction module. We got the LAB coordinates, threshold on the L coordinate, and used that score to estimate the skin tone range in a beauty image. And this was launched in production. It led to several wins. We heard positive feedback from our users who saw their experience improve, in particular in the darker skin tone ranges, and that led to engagement on more diverse content on the platform. However, over time, we started noticing issues of performance with the closed box version based on visual inspection. And in order to make progress, we needed to actually quantify the extent of the issue. So we collected a diverse data set that a specialist labeled, and we conducted an evaluation of the closed box system on this diverse data set. And in this image, the confusion matrix reveals, for example, that there is a major coverage issue for the closed box prediction in the darker ranges. And we also noticed performance disparities in the granular precision, recall, and F1 score per skin tone ranges. So in an image, this is how it looks like. At the top, you have the ground truth data set labeled by a specialist of image beauties. And the middle shows how the closed box understands skin tone ranges for these images. And so you see the coverage issue for the darker range. And it also had trouble distinguishing skin tone accurately for many images. Now, to understand why this was happening, we conducted an error analysis of the components of the system. The top right corner shows the score distribution for each skin tone range, and you can see that those score distributions are not really separable. They overlap quite a lot, and the thresholds were out of phase with the diverse data. And this type of issues can be amplified, for example, by shadows and challenging lighting conditions in the images. When we looked at the output of the face detection module, we realized that the coverage issue for darker skin tone ranges was coming from there, because the face detection module was failing to detect faces for many of the darker range images at much higher rates than for lighter skin tone images. And that type of bias in face detection technology has been studied and documented by Joy Buolamwini and Timnit Gebru in the gender shade study. And so we reached the conclusion that there was no amount of post-processing for fairness that we could do on the output of this closed box system that would fix those upstream biases that were built in. And so we needed to build our own system end to end. And so this is what we did. And our first in-house version, we also developed a system with several computer vision components. After exposure correction, a face detection extracted facial landmarks such as eyes, nose, mouth, and segmented them out, and then output a skin mask. In the case where a face was not detected, we used a hue saturation value processing module that allowed to detect patches of skin pixels in the image. Then that skin mask is fed into a color extraction module. We generate the LAB coordinate, compute a nonlinear function called the individual topology angle, and we pass that into a fairness-aware tuning phase that took as input a diverse data set to finally output the skin tone range. And when we evaluated the performance of this on the diverse data, it looked much better. The confusion matrix was closer to a diagonal and much more symmetric. The score distributions were more separable, and the per class precision, recall, and F1 scores were not only higher for every class, but also the disparities between the classes had reduced, meaning that we had reduced bias in performance. Now, in an image, you've seen the top part of this image earlier. The bottom row shows how the performance of the in-house visual skin tone progressed. While it's not perfect, we have made a lot of progress with respect to the closed box version. Now, this is not the end. Even our first version of the visual skin tone was still making errors, and we learned from those errors. So, for example, extreme lighting conditions are quite challenging. Occlusions such as beards and sunglasses can lead to errors. Then the pandemic happened, and it caused a surge of face mask images in Pinterest data, to which the model had to adapt. In some images, you have multiple faces or a combination of faces. In other images, the face is not visible, or there is no face at all because they have other body parts in the image. And so these cases prompted us to search for a more robust approach. And we invested in collecting our largest and most diverse data set yet for skin tone, including images from previous errors, partial faces, and body parts, to be able to handle new cases such as nails or hands, and images from not just the beauty, but also the fashion corpus and international locations. And for the system to handle more complex images, we actually decided to move away from face detection entirely, and we experimented with different architectures. So first, we used an approach that learned the skin tone range directly from the raw image pixels using convolutional neural networks. And that outperformed the V1 when evaluated on this larger, more challenging data set. Next, we leveraged the multitask visual embedding model developed by the computer vision team at Pinterest. That model is used for other important applications such as visual shopping and lens at Pinterest. So we added a skin tone classification head and used that to predict the ranges. And when we evaluated this approach on more complex data, it outperformed not just face detection, but also the ResNet across all metrics, while performing similarly, for example, across genders. And so the improvements in the skin tone signal gave us the confidence to expand beyond beauty to the fashion use case and to make skin tone ranges more prominent in the product and to launch internationally in 19 countries. Now, we built on our learnings on bias mitigation from our previous work on skin tone ranges to develop hair pattern search. So this this inclusive feature, is also powered by a computer vision model trained on diverse data to understand the hair pattern visible in an image. And to define the hair pattern categories, we consulted with hair experts who work with Black, Indigenous, and people of color, including Naïma Lafont, who is a Pinterest creator and also the artistic director for Amica, a hair brand. And their guidance, the help of our hair and beauty specialists, along with our user research team, informed our technical engineering choices actually throughout development. So to mitigate bias and ensure consistent performance of the hair pattern model across different segments of Pinterest content, we again collected a diverse set of hair images across hair patterns, skin tones, genders, and hair-related interests. We integrated hair pattern prediction into Pinterest's latest multitask model, again developed by the visual search team, that leverages the state-of-the-art vision transformer model, and also our investment in our computer vision infrastructure, because we need to scale to billions of images. And we iterated multiple times, augmented the data, and retrained the model to make it learn from its errors. And so to conclude, through this work, we gained many benefits from the inclusive AI projects. We improved user representation and content provider exposure. We are leveraging this work to understand the diversity of our content and increase the diversity of our corpus, as well as how it surfaced across Pinterest. We can build on this foundation to study and mitigate biases in other machine learning models for embedding, retrieval, and ranking. And it has helped us grow our inclusive product experience to other surfaces and globally. And I'll reiterate that really those challenges go beyond engineering, and they really require a multidisciplinary approach where engineers collaborate with product, inclusion and diversity, legal, user research, a set of people who have actually a variety of skills. And most importantly, I would say keep listening to your users and take their feedback into account. And so I'll leave you with words from our users, from our pinners, and I can take questions.
Wonderful. Thank you so much. This is such a fantastic talk. Thank you, Nadia. And I wanted to ask you, with respect to privacy, as you're narrowing down, because I know that that's also one of your big um, one of your big areas of interest. Once you're starting to narrow down more and more, hair color or preferences for this and that and the other, um, obviously you're sort of winnowing down the set of people you're talking about, right? And also even the clothes. These are the kinds of clothes we wear here in winter in the East Coast, or if people are always wearing nice, fun, short-sleeved, cool clothes. So, do you have a feeling right now as to sort of the privacy, the trade-off between being able to be more inclusive, but in effect narrowing down the choices better tailoring, and the privacy aspects?
So yeah, I can comment on that. So we take our users' privacy very seriously. One aspect that I would like to mention is that the skin tone ranges or even the hair pattern work is not done on the user side, but purely on the content side. So those models are not run on users; they are run on content images. We don't need to know the skin tone range of any one of our users. We are actually providing them control, and anyone can use any one of the skin tone ranges or any one of the hair patterns to search for content they are interested in. I'll also add that we do not target ads on filtered results by skin tone ranges or hair pattern for privacy purposes. So we are not trying to profile our users. We are giving them means of control on their experience and in a way that respects their privacy.
Okay, thank you. Thank you very much. I have a question from Manya. I wonder if you could share your insights on the next set of inclusive AI problems.
So, these systems, as I said, have several layers. And some of the work that like I described, for example, the skin tone ranges or the hair patterns happen, I would say, at the last serving layer. They are user facing, but there is a lot of work, I would say, to do in the earlier steps of the pipelines in ensuring, for example, that we make the content that surfaced diverse by default. A lot of the techniques start with putting re-rankers at the end of their chain, but then the re-rankers can only work with what's available there. They cannot fix lack of diversity, for example, that would happen in earlier stages. So I would say the next step is to actually move further back in the backend and improve fairness and diversity at ranking, retrieval, and even models for that are input to those layers. Yeah.
I see. Well, that makes sense. It's very interesting. Anthony has a question. What are the other prominent biases you see on the platform? For instance, overly specific clothes or products. I think this aspect of products and clothes products shown to users.
So there are different diversity dimensions you can consider. We started with skin tone ranges and hair pattern because it was helpful for our users, and we heard that there was a need for that. But you could imagine all sorts of other dimensions to focus on. It could be demographics, as I mentioned. It could be cultural or geographic based. It could be you could imagine, for example, in the food domain, diversity of cuisines. So it is. I would say fairness and diversity and inclusions are very context and domain specific. It's not like just a generic answer for every case. So it is dependent. Yeah.
Okay. Thank you very much. And this gets us exactly to our 1:30. I just want to thank again very much our speakers. I want to thank all our attendees and again, the whole staff at the C3AI Institute for allowing us, giving us this fun assignment. And with that, I look forward to seeing you all tomorrow at the same Zoom link, same times. And thank you all. Thank you.
Thanks a lot, Miriam. Thanks, Nadia. Bye.